Hello everyone, I am Bhargav. Today I am presenting PDIP, Priority Directed Instruction Prefetching. This is a joint work by Sankara, Gilles, Jared, Andre, and Professors Dean Tullsen and my advisor David August. So today I'm going to take you through a journey of Computer Architecture 101. Let's get started. So modern server workloads have large code footprints, due to which they face huge front-end bottlenecks. So one of the major reasons for this bottlenecks is instruction cache misses. To tolerate instruction cache misses, modern processes implement decoupled frontend. To understand what a decoupled frontend is, let's start by looking at traditional frontend. So in a traditional frontend design, address generation unit is completely within instruction fetch unit. So in this design, address generation unit is limited to predicting only one branch at a time. So when a fetch engine stalls, address generation unit is also going to stall. To address and notice that address generation unit does not depend on fetch engine. So to address this issue, you can decouple address generation unit from fetch engine. So this is a key idea. It allows you to keep going down the predicted path. This is the key idea of decoupled frontend, and this has been published in 1999, and commercial designs have been using it for a while. And so to communicate between address generation unit and instruction fetch unit, now a fetch target queue is inserted. So a prefetcher would take a look at FTQ entries and starts issuing prefetches in the predicted path. In this design, notice that even if fetch engine is stalling now, branch prediction unit can keep predicting in the predicted path. So okay. So notice that if you were to have a perfect prediction, so you'll never see any stalls. Unfortunately, that is not the case. To understand the impact of decoupled frontend, we implemented FDIP model in Gem5's O3 CPU execution model of Gem5. So here is a plot showing 16 data center workloads, and since the performance of FDIP depends on branch prediction unit, we made a lot of fixes to Gem5 and also improved branch prediction unit. And after all these fixes, we see 27% geomean speed up across 16 data center workloads. And the parameters are used close to Alder Lake-like CPU as shown on the left in the table. So to understand the effectiveness of FDIP, so let's look at by a common example. And so here is a common case of FDIP. In this example, all the new entries are added at the tail end of the FTQ. So because address generation unit can keep feeding FTQ with address in the predicted path, this is most common case where you keep adding new entries at the tail end. And here a new entry R14 is inserted at the tail end of the FTQ. And a prefetcher is going to take a look at that FTQ and is going to issue a prefetch to R14. So a request is sent. And imagine after probing iCache, you realize that R14 is missing in iCache. Now you need to forward this request to L2. Notice that in this example, head of the FTQ is ready, so fetch is not going to stall in this case. After a few cycles, R14 moves closer to the head. Now, imagine we get a response for R14. So in this case, notice that even though R14 missed in iCache, we haven't paid any penalty for R14. So by completely hiding the latency of R14. So if you have a deep enough FTQ, you'll be able to hide cache miss latency of many iCache misses, and which is a key idea of FDIP anyway. And that's why FDIP is very effective in getting very good performance. So let's take a look at uncommon case. What happens if you flush your FTQ? So yeah, here is the case. This typically happens after resteer. So when you have to resteer your pipeline, you flush everything and restart at head of FTQ. And now you're going to add new entries at the head. So imagine now, again, we are going to do the same process. We are going to issue a prefetch. And if it is a miss in iCache, now you are going to pay the penalty of miss of R0. So in this case, R0, the fetch stalls till R0 is serviced, and all the stalls are going to be exported to the backend. And these lines are considered front-end critical lines. So how often this happen? to understand this, let's look at the distribution and big impact of a small set of lines. So the title anyway gives away what I'm going to show. But anyway, let's look at the distribution. Here is a distribution of non-FEC lines and FEC lines. So we consider line to be FEC, which is front-end critical, if it has exposed front-end stalls, as well as back-end is doing nothing. So if you have a stall which is, even though your front-end is not doing anything, but if you have enough instructions in the queue, you can still sustain that latency, but we only consider those lines which actually cause front-end as well as back-end to be free. So in this case, we show it is to be 10%. And to understand the impact of this, let's look at the distribution of decode starvation cycles. It shows that FEC lines are contributing to only 10% are contributing to 61% of all stalls in the pipeline. To understand the performance impact of it, let's look at what if we could ideally prefetch these FEC lines. So here we are going to look at a configuration called FEC ideal. In this case, you are going to pay the cost of FEC line first. You need to identify a line first, and then you mark it in the L2 cache. And when you see the same line second time, we prefetch as if it is coming from L1, paying no extra additional penalty. So in this case, we show FEC ideal is going to give you 5% geomean speedup. And since iCache misses are a problem, let's try to scale iCache and see how much we are going to get. And now it shows that it's only going to give you 0.7% of geomean speedup. This is because FEC lines are a small portion of all lines. So your replacement policy is not aware of the critical lines versus non-critical lines. Even though if it is aware of this, so at times it's likely that the volume of non-critical lines is high. You might be evicting critical lines. So then how do we build a prefetcher to prefetch FEC lines? Now I'm going to show an example composed of what I've shown before. In this case, assume we see these cache lines in the decode stage of the pipeline. And here we see cache lines A, B, C, D. And we have a branch misprediction at line B. And then we have C and D, which are in the wrong path. And now you pay resteer cost. And then you go down the correct path. So here we see PQ, and the cache line R is actually missing in the iCache, which is like a more common case. You go down the conditional branch, and then the first few lines are available, and then you miss in the iCache. So R, in this case, R is an FEC lines. And this example, again, it clearly shows that FDIP struggles when we have iCache misses in the resteer path. So FEC, R is an FEC line, and which is caused by stall causing event, which is a resteer event by cache line B. So the key idea of PDIP is to associate stall causing event with FEC line. So in this case, we want to associate B with cache line R. Now I'm going to show how we are going to update metadata table. So like any of the prefetching technique, for example, FDIP depends on BTB. So similarly, PDIP depends on a structure called PDIP table. And the idea is that we want to associate trigger, which is B in this case, with stall causing line R in this case. So we are going to insert trigger B with target R. Okay, here's the animation, yes. So now I'm going to a sequence of operation. When are we going to look up this table, right? So again, I'm going to walk through the same example as before. So now we see cache lines A, and then A is missing in PDIP table, so we don't issue any additional prefetches. Now we see B hits in the table. So we issue a prefetch to cache line target R. And in the meanwhile, rest of the operations happen. You go down the wrong path, C and D, and then you mispredict, and then you're going to pay the recovery cost, and then you go down the resteered path. So PQ. And now since we issued a prefetch for R long time ago, so now it would have arrived by the time we reached in the correct path. So thus, PDIP is able to overlap recovery cost with miss cost of R, and we are able to show a decent performance. So now let's take a look at how well PDIP performs. And here is the PDIP with various configurations. And here I'm showing 2 times IL1 and related work called entangling instruction prefetcher, PDIP, and FEC ideal. So, and the value shown in the parenthesis is the size of the metadata table that we are using, and it is 46 kilobytes and 44 kilobytes in case of PDIP. So here, PDIP achieves up to 4.6 times of doubling the iCache and 61% of FEC ideal configuration. In conclusion, PDIP is the first criticality-aware instruction prefetcher. PDIP complements FDIP by mitigating stalls when FDIP struggles. So PDIP achieves an overall geomean speedup of 3.2% with the 44 kilobytes of hardware budget. Thank you. I'm happy to take any questions now.
I should have mentioned that this paper is one of the best papers. But yeah, questions.
Hello, Erasmus from USA. Great work. A question I have is that you left some performance on the table in comparison with ideal. What do we need to do to get there?
I mean, the ideal is such a config where you might not be able to prefetch in time. Even though we show various configuration, even though you try to increase the table size, you're not going to get much because it's plateaus at some point, right? So an ideal config is highly unlikely to achieve because we basically faked it in the simulator to as if we are getting it out of Akash. But even if you scale your structures, we actually, I've shown scaling the sizes, right? But the problem with doubling the iCache is that they fit in, they are in the critical path. So we are not accounting even for the latency increasing in the pipeline. We're just plainly increasing, you're not seeing performance. And I don't think it's easy to get rest of left of the headroom there. Right.
I guess I can have a question. So do you have any insight on why these critical lines were not prefetched by FDIP? Is it because of their branching behavior is complex, or is it something else?
Yes, that's exactly right. So if you have an infinite BTB, you will never see any improvement with these techniques because the branch footprints of these workloads is over 20,000 branches. And you cannot hold on to all of them, and you cannot make your BTB without paying the penalty of latency. So BTB is around 12K or like 16K, somewhere around that. So that's one of the reasons BTB forgets these branches, and then we are only trying to capture those where we actually pay the penalty, right? And it's only a small portion, not every, you don't need to hold on to every branch, but if you can hold on to those branches which are critical, as in the mispredictions and conditional branches, and this behavior is kind of consistent across the program behavior. Like we have, since it is large code footprint, you kick out a lot of lines from L1 and then again you bring them back, but BTB forgets them. And we don't know that, I don't have that information anymore.
Let's thank the speaker if there are no more questions. Next up, we have Hannah Lin from Google. She is a software engineer at Google and a PhD student at University of Washington. Her research interests are in hardware-software co-design for data center applications and in using ML for systems problems. And today she's going to talk about Limoncello, designing prefetchers for scale.
I think it's going through. Let's show that one. Thanks, Akanksha, for the introduction. As Akanksha mentioned, I'm here to share with you all about Limoncello, a software system for prefetching data for scale. As you all know, Google owns some of the largest data centers in the world. These data centers are placed in over 10 different countries across multiple different continents, and they consist of millions of servers. At Google, we care a lot about running these data centers efficiently and making sure we use our machines wisely. And one way we do that is by making sure that our machines run at peak performance and are always loaded with workloads. So one way we measure how efficient our data centers are is by using machine utilization rate. We have this target machine utilization rate of 70 to 80%. Recently, we found that a lot of our machines were sitting around underutilized. there was this 20 to 30% utilization bottleneck that we found, and a lot of our machines weren't able to reach that 70 to 80% target utilization rate. So we started looking into this, and we found that we had some issues with memory bandwidth. Memory bandwidth was often running low on our machines, and as a result, we weren't able to run as many workloads as we should be able to. So naturally, we next began to look into what was taking up all this memory bandwidth. And we found that a big part of the problem was our hardware prefetchers. Typically, you expect that hardware prefetchers improve performance by bringing data into cache. And indeed, we do see a lot of work showing us that that is what often happens, and hardware prefetchers do have the ability to increase cache hit rates by 30 to 40%. However, at Google, we've been seeing that our hardware prefetchers often cause performance regressions for us, and they were increasing memory bandwidth usage, and as a result, blocking our data center utilization. And so we started analyzing this a little more, and we found that there are some very interesting relationships between hardware prefetch activity and memory latency. This slide here shows a standard memory latency curve that you see. On the y-axis, we have load to use latency, and along the x-axis, we have memory bandwidth utilization. As you move along the x-axis to the right and increase in memory bandwidth usage, you eventually start hitting this exponential rise in memory latency. So this is our standard memory latency curve. Now let's take a look at what happens when you turn on or off our hardware prefetchers. This curve currently shows conditions when all hardware prefetchers are off. If we introduce hardware prefetchers and turn them on, we see this curve rise by up to 15%. This means that if you're moving along to the right and increasing in memory bandwidth usage, you start hitting this exponential rise in memory latency more quickly than you would if the hardware prefetchers were off. So from this, we see that our hardware prefetchers were working rather inefficiently and unnecessarily taking up our memory bandwidth. So with Limoncello, we take this as one of our main insights in how we design our solution. Limoncello is a hardware-software co-design solution that consists of two components. Hard Limoncello configures hardware prefetchers, and soft Limoncello inserts software prefetchers. I'm going to start off by first describing hard Limoncello. Hard Limoncello is designed mostly around the memory latency curves that we just saw. In hard Limoncello, we choose a lower threshold and an upper threshold, and we dynamically disable hardware prefetchers based on memory bandwidth usage levels. When those usage levels are low and below the lower thresholds, we keep our hardware prefetchers enabled, and when they exceed the upper threshold, we then turn off our hardware prefetchers. And when that memory bandwidth usage levels falls back down below the lower threshold, we turn our hardware prefetchers back on again. So if you're looking at this, you might be a little concerned about the green portion where our hardware prefetchers are disabled and wondering whether we see any code regress from turning off our hardware prefetchers. And that would be indeed a very valid concern because we do see code regressions from turning off our hardware prefetchers. In this figure here, we have fleet-wide CPU cycles along the y-axis, and the blue bar shows standard conditions where hardware prefetchers are on. And this is the CPU cycles for a certain set of functions that I will describe in more detail very shortly. But notice how in this figure with the yellow bar, when we turn off our hardware prefetchers with Limoncello, we see the slight performance regression, and there's more CPU cycles spent in these functions. And so due to this code regression, we introduce soft Limoncello, which adds in targeted software prefetching for code that experiences regressions when hardware prefetchers are turned off. Soft Limoncello identifies these prefetching targets using a hardware ablation study. For this hardware ablation study, we take all the machines in our data center, we select a small subset of those machines, and we turn off hardware prefetchers on those machines. And then at Google, we have this fleet-wide profiler that goes over all our machines and periodically randomly take samples of performance metrics from those machines. From this fleet-wide profiler, we're able to get this very nice function level view of what happens when we turn on or off our hardware prefetchers. So going back to that bar chart, here we have the bars again broken down by a few function types. Along the y-axis, we have increase in CPU cycles. And from our profiling data, we're able to see that a large majority of the functions that regress are data center tax functions. These are functions like compression, data transmission, hashing, and data movement that are very common in applications in data centers and are seen as a sort of application overhead in data centers. And nicely, these data center tax functions are also often prefetch friendly because they typically act over contiguous blocks of memory. And they're common building blocks to many applications, which means that if you insert a single prefetch into one of these functions, you're able to benefit a lot of applications together. And so with soft Limoncello, we use these data center tax functions as our primary software prefetching targets. Soft Limoncello is able to fit very well with hard Limoncello because hardware and software prefetching work a little differently and complement each other well. Hardware prefetching is speculative, which means that you don't have to determine by yourself where all those prefetchers are going to go, and the hardware prefetcher makes guesses about where your data access is going to happen. But this also means that sometimes those guesses are incorrect, and it may prefetch incorrectly. Hardware prefetchers are also very coarse-grained. You can't turn them on or off for just like specific lines of code, but they act on entire cores. In contrast, software prefetching is very specific and fine-grained. The program is what specifies what is going to be prefetched, and so programmers or compilers can insert software prefetchers for just certain objects or certain data accesses that are known ahead of time. And so we use this key insight in soft Limoncello to design software prefetching such that it is very targeted and can compensate for the performance regression that happens when hardware prefetches are disabled. And so now the full Limoncello consists of hard Limoncello, which dynamically disables our hardware prefetchers, and by doing so, reduces our memory latency. And then we also have with it soft Limoncello, which inserts targeted software prefetching to improve our cache hit rates. And with hard and soft Limoncello together, we've been able to see huge wins on our data center fleet. Here in this graph, I have along the y-axis increase in application throughput, and along the x-axis, 2 different CPU utilization bands. From rolling out Limoncello across Google, we've seen application throughput improve by 10%. We've also seen improvements in memory bandwidth usage. Here we have 3 different percentiles and improvement in bandwidth usage along the x-axis. And on average, we see that our memory bandwidth usage improves by 12%. Similarly, our median memory latency also improves by 12%. Again, we have 3 different percentiles in this figure, along with improvement along the x-axis as measured by percent decrease in memory latency. And finally here, taking a look again at our data center tax functions, we see from, as before, when we insert hard Limoncello and disable hardware prefetchers alone, we get this rise in CPU cycles. However, if we add in soft Limoncello and introduce software prefetchers as well, we get an overall decrease of 2% in these CPU cycles of these functions. So in conclusion, at Google, we've been seeing that our hardware prefetchers can actually cause performance degradations for our systems. And with Limoncello, we introduced dynamic hardware prefetching, which is able to decrease our memory latency. And we've added to that targeted software prefetching, which increases our cache hit rates. With both of these 2 things combined, we've been able to reduce memory bandwidth bottlenecks across our data centers in ways that we could not have achieved with either hardware or software prefetching alone. And so overall from this, we've been seeing that hardware and software co-design is very promising for improving the performance of our data center systems. And thank you. I'd be happy to take any questions.
Hello, thank you for the great talk. I am from EPFL. So when you're using software prefetchers, how do you know which lines to prefetch for that function?
Our profiling is able to do attribution, performance metrics attribution by line. And with that, we do get some metrics on last level cache misses per line and also CPU cycles. And that gives us indication of where those prefetches should go. And then we also go through a process of iteratively testing different prefetches for these functions. We do both micro benchmark testing as well as broader load testing to verify that the prefetches that we insert are actually improving performance for these functions.
Okay, thank you.
Gilles Pokam, Interlabs, great talk. I like the subject. I have a question. So when you say hardware prefetcher degrades performance, do you have some insight of why? I mean, is it because of the misspeculation? What's the reason? I wanted to have some insight to the motivation.
I think part of the reason is definitely, like you said, hardware prefetchers can be inaccurate and they don't always make accurate guesses of where the prefetch should be. And then in addition to that, we think that hardware prefetchers can also be pretty bursty and also cause cross-chiplet interactions that can make them bring in more performance regressions on the workloads.
Okay, thanks.
Hello, I'm Xiaoyang from eNoiTech. So I have a simple question. How many different kind of hardware prefetcher you consider in this work? So if you want to disable them, just disable them together, or you choose something? I'm not sure.
For this work, we are disabling all the hardware prefetchers together.
Okay. Yeah, I'm just thinking some different hardware prefetcher may have different performance or accuracy, coverage. So yeah, just want to make sure that. Thank you.
Hi, I'm Huyun from Yonsei University, and I have one question regarding the soft limoncello. To my understanding, soft limoncello can be implemented using compilers. So is this done on static time or is it done on dynamic time?
For Limoncello, our soft Limoncello is not, we're not inserting the prefetches with compilers. That's definitely something that could be done, but we are doing the software prefetching manually. So these are inserted by developers.
So it's safe to say that it's implemented in runtime, or prefetching is implemented in the code beforehand, before the execution?
It's implemented beforehand,
Okay.
before the program is running.
Okay, thank you.
Okay, let's thank the speaker. Next, we have Linja. She's a third-year PhD student at University of Utah. Her interests are in computer architecture, AI and machine learning, and genomics. And today she's gonna talk to us about PATHFINDER, which is a practical real-time learning for data prefetching. And we're running ahead of time, so bring your questions.
I have used this one works for me.
Okay, yeah, that's right.
Yeah.
Yeah, it works.
Great. Thank you for the introduction and thank you for your patience. I'm Lin from University of Utah. So today I'm going to show you Pathfinder, practical real-time learning for data prefetching. Data prefetching is a well-studied problem. There are many different types of prefetchers. Some prefetchers are easy to implement, but the performance is not optimal, like very easy one, the next line prefetcher, and also the spread prefetchers. Some prefetcher have great performance, but the implementation cost is high, like a temporal prefetcher and then the neuron prefetcher. The neuron prefetcher even, implement in practical. So the ideal solution is to build a prefetcher that has low implementation cost while maintain good performance in terms of IPC, accuracy, and coverage. But the ideal solution is always hard to achieve, so we propose the Pathfinder. We are pursuing a design point that is competitive with the state-of-art prefetchers while having low implementation complexity. The prior state-of-art neuron prefetchers, they have good performance, but not practical in the real life due to two main reasons. The first reason is the neuron prefetcher are always collecting the training traces and the inference traces separately. And the second reason is they are required to do training on a GPU for hours to have a trained model ready to deploy on the inference trace. Instead, we are trying to do training and the inference on the fly. After working on a short amount memory access history, we are predicting the next access. To achieve this, we are using the spiking neural network with SDDP and supervised learning rules. With these two techniques here, SN plus SDDP, Pathfinder can do online learning. There is no need for us to do training and inference on two separated epochs. And also we can achieve competitive performance, exhibits 2% better performance than PISA and 1.7 advantage over Voyager. Pathfinder also has low overhead. It can be implemented at 0.5 watt and an area footprint of only 0.23 millimeter square in 12 nanometer technology. Sorry. Okay, let's dive into the details of how Pathfinder works. Pathfinder is trying to learn the delta patterns within the individual pages. When it see two offset from two consecutive memory access in a page, it's able to calculate the delta between these two. Like here, when I see the when I see the offset 2 and then the offset 3 in a page, it recorded the delta 1. And then when I see the next offset, which is 5 here, it record 2 here. So on and so forth. We also the same thing on the other pages as well. When we have 3 delta history point ready, we fit this pattern to SNN. With the training on the fly, the SNN can generate the prediction of the next delta, like 15 in this example. We have seen Pathfinder from a high level picture. Let's talk more about the key part of it, the SNN. So on the very top, we see the blue bubble, which is the processing neuron in the SNN. It will receive the voltage through the spectrum from the input layer. So the internal voltage of the processing neuron will increase, and otherwise it will decrease over time. The voltage keeps accumulating until it passes the certain threshold at a certain point. That will be an input-output spike generated. Otherwise, it will stay silent. Next, let's see how it works at the layer level. So whenever we got 3 delta history point, we convert them to a memory access pixel matrix with H rows and then D columns. In our default setting, our H equal to 3, which means we have 3 delta history point, and then D equal to 127, which means because our delta range is from -63 to +63 when we're looking for the deltas within a page. The input neuron with widely pixel information encoded will send to spike train to the processing neurons. And then the weights between the input layers and then the processing layers are randomly initialized. But one of the neuron is predisposed to firing first when it sees this input pattern. We will go on to strengthen the weight such that when this input pattern is seen again, this neuron is again a clearly winner. Later, when it see the next observed the delta, which is 15 here in this example, we will label this neuron. So it predicts a delta of 15 when it see more patterns. Next, let's see more about how Pathfinder updated the weights between the input neuron and then the processing neuron using the STDP learning rules. The spike timing is very important to the STDP to make the decision of either strengthen the weight or weaken the weight. So one spike from the input neuron triggers the output neuron generate an output spike. The STDP will strengthen the weight between the input neuron and the output neuron, which means the input spike is an important spike to the output spike. Otherwise, there is an output spike already triggered by some input spike. And at the next moment, there is another like input spike coming in. The weights between these two neurons will get weakened. STDP is a simple, fast, local training algorithm that enable us to do data prefetching on the fly. Now let's take a look at a simple example of the patterns being tracked and updated in Pathfinder. In this example, delta stream, the delta from different pages are colored with dark gray, gray, and light gray. So when we see the first 3 delta, 1, 2, 3 here, we convert it to memory access pixel matrix and feed them into SNN. And then the SNN has a neuron firing, which is 6 in this example. For this pattern, we updated the corresponding entry in this training table and also in this inference table. At that moment, there is no label for this neuron 6 yet. So we won't make a prediction at this point. We will label it at a bit later time. So we will keep seeing the new patterns coming in, convert it to pixel matrix, feed them into SNN, and update the entries in the table. We follow the same steps for all these patterns. Sooner or later, we see the same pattern 1, 2, 3 show up again. Follow the same process as we do previously. And then we found that the SNN triggers the neuron 6 firing again. But there is still no label for that neuron yet. What we are going to do is we will label it with the corresponding next delta that follows this pattern. And then when the next time when the Pathfinder see this same pattern showing up, we are able to make the correct prediction. Also, we will initialize the confidence in this for this entry in the inference table of this neuron label pair to 1. When it makes the correct prediction, the confidence will increase by 1. Otherwise, it will decrease by 1. So we use 3-bit separated confidence counter range from -2 to +5 to make sure we can remove and the outdated label and then relabel the neuron when the code phrases changes. We have synthesized the circuit and show that it can be implemented at 0.5 watt with an area footprint of 0.23 millimeter square in 12 nanometer technology. The high memory consumption part and time consuming part is the weight buffer that store the weights for the corresponding neuron. And then the timer part that control the spike tree. However, we do have lots of engineering knobs that can twist to reduce the overhead such that we can work on the reduced range of delta instead of full range of 127. And also we can reduce the time interval to see more. So you will see more results that tuning different knobs that's shown in our paper. For the results part, we are comparing against a range of recently published state-of-art prefetchers that include history-based delta prefetcher, the temporal prefetcher, 2 LSTM-based neuron prefetcher, and then 1 reinforcement learning-based prefetcher. So each one has its corresponding emphasis. So you can see more details about our baselines in our paper. So on the average, Pathfinder achieves 2% better performance than PCA and 1.7 advantage over Voyager. Since Pathfinder is also a selective prefetcher, we are also trying to ensemble Pathfinder with other type of prefetcher, like Next9 and SSB to fill out the prefetch budget while keeping the prefetch degrees equals to 2 in our default setting. That also helps us improve the performance as well. Our work is currently open source and get the artifact evaluate. Thank you for your attention. I'm happy to take any questions. Thank you.
I'll get us warmed up. So I was curious, it's really fascinating to see SNNs be a replacement for artificial neural networks.
Yeah.
I was just wondering if what kind of challenges did you encounter in training SNNs? How different or difficult it is from artificial neural networks?
Yeah, sure. So because comparing against the traditional like LSTM or even larger models, it's not using the really hard statistic reason and algorithm is the accuracy we have came across really. We are trying to lots of different ways to improve the prediction accuracy, and also our input like matrix is really sparse. It's hard to, it's not really like the image recognition task. It has a lot of valid pixels. We only have 3 valid pixels in our sparse matrix, and it's hard to force the SNN to generate like output spec for every single like input. So we have trying to tuning like different parameters, how to make sure the SNN can generate valid prediction for every single input that we have like tried for a while. And also yeah, the training time for us, like we are using the BandSnipe, the out of shell as a simulator, and it's writing by Python. We are trying to convert it to like a C or C++ to make it faster, but we not ready to get it done, but we would like to try it if we get time to make sure our simulation time can get a little bit faster. Yeah, so that's pretty much we have came across the challenges. Thank you for your questions.
Thank you. We have time for maybe one more quick question if anybody has. Otherwise, let's thank the speaker. Thank you.
Thank you.
need to change the displays. That's in another display. Yeah, so it's yeah. I'm going to switch.
Our next speaker is Shashank Anand from ETH Zurich, and he's going to talk about skip it, take control of your cache.
Hi, everyone. I'm Shashank, and I did my master's at ETH Zurich, and I'm here to present the work done as part of my master's thesis. Skip it, take control of your cache. So what exactly is the problem we're trying to solve here? There is a lack of work on how to design a microarchitecture for user-controlled write-back in modern out-of-order CPU cores. So to solve this problem, we aim to design, implement, and evaluate an infrastructure for user-controlled write-backs. And on top of that, we investigate optimizations that can solve redundant write-backs that are issued by the programmer. So as the first part of our work, we designed the flush unit, a microarchitectural unit that is integrated with the boom out-of-order CPU core. And as the second part of our work, we introduce skip it, a novel hardware mechanism to catch and optimize away redundant write-backs already in the L1 cache. We evaluated on an FPGA, and we benchmark our flush instructions against commercial x86 and ARM chips. And we compare our hardware optimization skip it with state-of-the-art research. Results, we outperform x86 and we perform close to ARM with our new instructions. Additionally, our hardware optimization performs close to the state-of-the-art solution with none of the software overheads. So this is what the rest of the talk is going to look like, and let me get right to the motivation. So why exactly do we care about being able to flush a cache line from the program? One, for DMA, we need to explicitly write back cache lines to make changes visible to the DMA clients. And additionally, to ensure consistency in NVM or remote memory, we need to explicitly write back to maintain this consistency. So for some quick background, I've been talking about user-controlled writebacks and cache management, but what exactly do I mean by them? Let me define these instructions. So by cache management and user-controlled writebacks, I mean the ability by the programmer to flush a cache line all the way onto DRAM. There are usually two kinds of writebacks, invalidating and non-invalidating writebacks. In out-of-order cores, these are generally asynchronous, and the programmer must explicitly fence them to force synchronization. The instructions have been part of our commercial processors for quite some time, and they are found in all modern commercial implementations. However, the equivalent instructions in RISC-V, CBO flush and CBO clean, that have been introduced as part of the ZigBomb ISA extension remain unimplemented in the open source course. So we do our work all on the Berkeley out-of-order machine, the Boom core. The Boom is an open source out-of-order CPU core designed at Berkeley with a pipeline that looks something like you see on the slide. We don't have time to get too much into the details of this, but I will say that our work focuses on the decoder unit to add support for the new instructions. And the bulk of our work is in the L1 data cache, as can be seen in the pipeline. All right, so for the first part of our work, the flush unit, this is a picture of the L1 data cache of the Boom core. As you can see, there are standard MSHRs, the SRAM arrays, and the write-back unit and the probe unit that take care of cache coherency and cache line eviction operations. And there are the tile-link in-chip communication channels that go in and out of the L1 cache. Our flush unit plugs into the L1 cache and is the unit that is responsible for handling the instructions that are issued from the load store unit. So let's get a bit deeper into the flush unit. So this is a high-level overview of what the design looks like. Oops. We have the flush queue. The flush queue is responsible for buffering incoming flush and clean instructions to take the load off of the actual flush unit itself during times of high contention. And then we have the flush MSHRs, the actual worker units that are responsible for executing the flush the instructions. These MSHRs do the work of figuring out whether it needs to read data from the SRAMs, replying, sending the message upstairs, so to the higher level caches with the updated data, and waiting for a response back. The flush counter tracks all flushes and cleans that are outgoing in the flush unit. This is important because the flushing signal out of the flush counter is plugs into the load store unit to help the load store unit figure out when it should be done with a fence instruction. So some hardware optimizations that we implemented as part of designing the flush unit was, one, any loads that come in that have outstanding data in the flush MSHRs are allowed to forward this data from the FMSHRs without having to wait for the flushes to complete. We coalesce adjacent CBO clean or CBO flush instructions that are right after each other in program order. And additionally, stores are allowed to jump any pending non-invalidating write back that are outstanding in the flush MSHR. And the final part of the design, cross-core interference. Because the flush queue buffers these flush and clean instructions, any amount of time may pass before these instructions are dequeued from the flush queue and are ended up being processed by the flush MSHRs. The metadata in the flush queue must be accordingly updated with the response to cache coherency events. These ready signals are implemented to signal the flush unit to wait, or the other way around, for the flush unit to signal the probe and the cache line eviction units to wait in case there are transactions going on to the same cache lines. And additionally, these invalidate signals are used to update the corresponding queued instructions within the flush queue in response to any changes as a result of cache coherence or cache line eviction events. Now, for the second part of our work, skip it, the hardware optimization. Imagine a program like this. We update X and Y at the beginning, and then we flush X and we flush Y. We know that these flushes must go through because we know for a fact that X and Y are dirty. Here now, then we dirty X again, and then we flush X. This must also go through because the data must be propagated to the main memory. However, this flush Y can be safely skipped because we know for a fact that we have already flushed the modified data of Y. So what do we want to do? We want to skip these redundant write backs in hardware completely invisible to the programmer. But this brings us to the question of why can't we simply use the dirty bit in the L1 cache and then just skip the write back using the dirty bit? Let's look at an example to see why that does not work. Imagine CPU 0 and CPU 1, each executing this very simple program. CPU 0 has X, CPU 1 has Y. So as you can see, they both modify their respective values. The dirty bit gets set and the updated value is written in their L1 caches. Then they each read the other's data. So CPU 0 reads Y and CPU 1 reads X. What happens first is that because they are both in modified state in their caches, they must first send the data to L2. So relinquish their cache line and revoke their permissions. Once L2 gets the updated data, then these are sent back to the requesting cores. And they both now have the new updated data that is taken from the other's cache. However, as we see over here, while the dirty bits of both of these are unset, we see that the L2 cache has modified data, and therefore we cannot skip this flush. However, we do not know if we can skip this flush or not, merely using the dirty bit of the L1 caches. Therefore, the dirty bit of the L1 caches are insufficient to solve the problem that we are aiming to solve. What do we do to solve this? We introduce a new bit called the skip bit, and we store it alongside the dirty bit of the L1 cache, for each cache line in the L1 cache. So now what do we do is that when each cache line requests a line from the higher level cache, the higher level cache responds with the status of its own dirty bit. So now, as we see, the skip bit is set in response to the dirty bit of the higher level cache. So if effectively the skip bit is the negation of the higher level cache's dirty bit. And now, based on this information, we know whether we need to skip the flush or not. And this skip bit is easily maintained using the in response to cache coherency events. For a more detailed proof, I would recommend looking at the paper. So finally, the results. We evaluate everything on the FPGA. We use a dual core sonic boom configuration, 32 kilobyte 8-way write back L1 cache, 512 kilobyte 8-way shared L2 cache. Our L2 cache is the DAS level cache. And we evaluated on FPGA running build root Linux with FireSim. So we see the effects of cache coherency, context switching, and virtual memory as well. So results. We compare the latency of our instruction with the commercial instructions from ARM and x86. We see that we perform quite competitively with the equivalent instructions, equivalent clean and flush instructions in commercial implementations. Here we compare the performance of skipit versus simply not using skipit in the boom core itself. And we see that we save around 20 to 25% latency. And finally, we compare skipit with the state-of-the-art software solutions. As we see here, Flit and Link and Persist are some of the software solutions to solve the same problem. We notice that skipit performs better than or close to these software solutions with none of the overhead required by software, and it happens completely transparently to the program. Thank you very much for attending my talk. There are a lot more technical details and proofs in the paper itself. I recommend you all to take a look at the paper, and all the code is open source, so feel free to play with our RTL. Thank you.
Since we have a very quiet audience today. I'll get started with one question. You didn't, or maybe I didn't catch it, the benchmarks you used for your evaluation. I was wondering how the opportunity for skipping scales with the number of threads in the application.
Yes, we actually have a equivalent benchmark in the papers as well. And skipit scales very well with the number of threads. As the number of threads increases, and it scales almost linearly. Oh, actually, yeah. There's actually a slide for it, I believe. Let me, no, it's in the paper. No, this is without skipit. It's in the paper.
Great talk. Thank you. Gilles Pokam, Interlabs. I was just wondering, are there any security implication with this instruction?
As far as we see, there are no security implications, as the flushing merely sends the updated data all the way to DRAM. And these are implemented, these have been part of our modern commercial processors for perhaps a decade or so. So as far as we see, we don't see any security implications as a result of these instructions.
Okay.
Hi, Jonas, Graz University of Technology. Great talk, thank you. You said that AMD is still slightly faster, right? Do you know if they implement something like skipit? ARM, I meant, sorry.
As far as we know, we're not aware of the way the proprietary designs look like. So all we can see is we measure our latency and we compare with theirs, and we perform competitively. So unfortunately, we're not aware of how they do their designs.
Okay,
but,
and another question, did you evaluate side channel security things? Like, is there any problem that maybe one program can detect if another program already flushed the cache line or something like that?
Yeah, we did not take a deeper look into side channels, but there was something we wanted to look at, as we had some in our related work related to security and side channels. But for this work, we were unable to take a closer look at side channels.
Okay, thank you.
Great talk. I'll ask a security question without asking a security question. So I'm just curious as to whether you think there's any opportunity for value-based skipit, which is to say, if you keep on writing back to the cache, i.e. making the cache line dirty, but the contents don't actually change, do you think that there is an opportunity to avoid writebacks in that case?
Yeah, absolutely. We would be able to, as part of future work, one thing we could improve the skip bit in is that we could maintain the skip bit with the response not only to cache coherency event, but with also in response to the value that is being written back. So we could compare the value being written into the cache line with the current value, and then appropriately update the skip bit as well.
Out of curiosity, did you ever profile something like that to get a sense for what the opportunity would be?
No, we did not profile anything like that, but that was that's definitely one of the future things that we can look at. Thank you for the questions.
Let's thank the speaker. Our final talk for this session will be by Yushuan Zhang. She's a PhD student at University of Pennsylvania. She's interested in bridging the gap between data center applications and server processor design through hardware and software techniques. And today, she's going to talk to us about robust profile-guided runtime prefetch generation.
Hi, everyone. Today, I'm going to present RPG2, Robust Profile-Guided Runtime Prefetch Generation. This work is in collaboration with Intel, UCSC, UW, Google, Columbia University, and UPenn. Out-of-order execution can hide latency for accessing R1 data cache, but it is not good at hiding latency for accessing lower-level memory hierarchy. Hardware prefetchers can only prefetch for simple data memory access patterns, but it's for short for prefetching indirect memory access or pointer chasing. Therefore, to address the performance degradation caused by data memory access, we must also rely on software prefetching. However, software prefetching faces several challenges. First, the computation of the address for prefetching, also called prefetch kernel, needs to be extracted from the existing code, which is hard. Second, prefetch has to be done at the right time to guarantee timeliness. For example, in this nested for loop, we try to insert prefetch to the inner loop. And we either prefetch for the data that will be used in the iteration that is 1000 run after the current iteration, or prefetch the data that will be used in the next iteration. For the former case, we might prefetch too early because when we really need the data might have already been kicked out of the data cache. For the latter case, we might prefetch too late because when we need the data might not be brought to the data cache. So here, the number 1001 denotes prefetch distance, and this prefetch distance reflects the degree of timeliness for data prefetching. And we want to have the optimal prefetch distance because the optimal prefetch distance can guarantee prefetch to be neither too early nor too late. However, to guarantee the timeliness of data prefetching is not an easy thing because this timeliness not only depends on the program itself, but also depends on the input of the program and the hardware. For example, in this figure, we run single source shortest path program on the Haswell machine with 4 different inputs. And from this figure, we can find that for different input, the optimal prefetch distance is different. There are also, what's worse, there are also cases where when we, for some of the input, the prefetch can improve performance. And for the other input, the prefetch can always be harmful to the performance. And the static compilers will not work for such cases because for some of the input, because the compilers has already insert the prefetch instructions to the binary, and there is no way to run the program without these prefetch instructions. So even if the prefetch ends up being harmful to the performance, to address these problems, we propose RPG2. RPG2 is a pure software system that operates on the running C, C++ programs, profiling them, injecting prefetch instructions to them, and tuning those prefetches to maximize performance. RPG2 can also respond when prefetch ends up being harmful and roll back to the original code. And here is how RPG2 works. First, we have the target process, and then RPG2 will profile the execution of the program. And then with the Intel PEPs, namely process event-based sampling, and to collect the last level cache miscount for each instruction. And then based on the profile, RPG2 will build optimized binary with the post-link optimizer bolt. And after the optimized binary is built, RPG2 will leverage a ptrace system call to pause the target process. And then RPG2 will extract the difference between the original binary and the optimized binary, which contains prefetch instructions, and inject this difference to the text section of the target process. And after this injection is done, RPG2 will leverage ptrace again to resume the target process. And at this point, the program will run with the run with the code that contains prefetch instructions. However, we are not done yet, because when we insert prefetch instructions to the text section, we randomly pick a number as the prefetch distance. So we still need to tune this prefetch distance to be optimal. Here is how we do this. We first measure the performance of the program, and then we change the prefetch distance by editing 4 bytes in the text section, which represents the prefetch distance. And then we measure the performance again and change the prefetch distance again. We repeat this procedure until we find the optimal prefetch distance. And at this point, we achieve the best performance. So after that, the program will run with the real optimized code. To implement such a system, there are still some issues needs to be addressed. When we insert prefetch to the text section, we not only just insert a single prefetch instruction, but insert 3 pieces of the code. The code that computes the address for prefetching, the code for bounce checking, and finally the code that cleans up the architectural state that is changed by the previous 2 pieces of the code. However, none of the existing static prefetch insertion compilers can generate a binary that contains these 3 pieces of the code for online code injection, because the static compilers will always insert prefetch instructions to the compiler IR code. And after these prefetch instructions are inserted to compiler IR, the compiler still needs to perform a number of optimizations before it finally generates the optimized binary. And these optimizations might significantly change the control flow graph of the optimized code. So it's hard for us to extract the difference between the original binary and the optimized binary. Hence, we're not able to insert this difference to the text section. Our solution to this is we directly insert the prefetch code to the binary code layout of the function without using any of the compilers. So in detail, we insert these 3 pieces of the code to the text section of the to the text section. And when these 3 pieces of the code are reflected to the control flow graph, they are the 3 pieces, they are the 3 binary basic blocks in gray here. And for the original code, it almost remained unchanged. So we only need to do very trivial edits for the existing code. And thus this approach is easier for us to perform the online code injection. Another issue we need to address when we implement this system is after we insert the prefetch code to the text section, the code size of the optimized function might get larger. So we might not be able to put this optimized function to the original function slot. And our solution for this is we inject our optimized function to a new location, which is outside the original text section. And this means we keep 2 versions of the function in the address space, the original function and the optimized function. The reason we still want the original function in the address space is because there are cases where prefetch hurts performance. And in such cases, we want to roll back to the original code. And if we keep the original copy in the address space, it's easier for us to perform this rollback. And the only thing we need to change in the original code is for all the call instructions, we need to, that points to the original function, we need to have them updated, because at this point, they need to point to the optimized function. The last issue we need to address when we implement this system is from the profile, we only have the information about which function, which instruction that causes the most number of last level cache misses. However, what we want to insert to the program is the prefetch kernel that contains a number of instructions. So our question is, how do we generate the prefetch kernel from just a single instruction? Our solution is we leverage LVM loop info class and bolts infrastructure to identify loops in the binary. And with the binary loop information, it's easy for us to identify the bounce check instruction and then generate the bounce check basic block. And similarly, we can traverse the binary loops to get all instructions that computes the address for prefetching and generate the prefetch basic block. With these two basic blocks, it's easy for us to produce the binary for online code injection. And we measure the performance of RPG2 and compare it with apt-get, the state-of-the-art profile-guided prefetch insertion compiler. And we put our result in two different groups, the speed-up group and the slowdown group. In the speed-up group, the prefetch can improve performance. And in the slowdown group, the prefetch can always hurt performance. So from this result, we can find that in the speed-up group, RPG2 can have a comparable speed-up to apt-get, while in the slowdown group, RPG2 can significantly outperform apt-get because RPG2 can roll back to the original code while the static compilers cannot. So for the overall performance, RPG2 can slightly outperform apt-get. In conclusion, in this research, we implement RPG2, a software system that can insert data prefetch at runtime. And RPG2 can achieve a comparable speedup to the state-of-the-art profile-guided prefetch insertion compilers. And it can also roll back when prefetch end up being harmful. We open source our code in this link. And if you are interested, you can also scan this QR code. That's all. Thank you.
Okay, interesting work. I have a question. A few slides back, you were showing this iterative approach to finding the optimal prefetch distance.
Approach to find optimal.
Which slide was it?
This one.
Yes, this one. So do you, how do you start? How do you decide that you're optimal? How many iterations do you usually take on average? And do you have a max number that you stop at regardless?
We start with a random number as the prefetch distance, and then we search from the space, and then we decide the upper bound and lower bound for the binary search of the optimal prefetch distance.
So in practice, how many iterations does it take before you find the optimal?
And actually, we have this result, but I didn't present it. So, oh, sorry, maybe we can. On average, it will be about 11 times for this prefetch edit. And then we can find the optimal prefetch distance. And the overhead is not very high because it's about 1 millisecond for each edit.
All right. Oh, thanks.
Michael Giordino, Huawei. Actually, this is what I was going to ask about. Can you talk a little bit about the how long it takes to do the optimizations and then the code insertion and restarting?
Yeah, for the code insertion, we pause the target process and then insert the prefetch code, which contains a number of instructions. So the time is longer than the prefetch edit because we only need to change 4 bytes for this case. And this is the time for code insertion is 3.9 millisecond on average for PageRank. And for the other workloads, almost the same performance.
Thank you.
We have time for, I guess I had a question here. So one of the challenges, at least at Google, that I've seen is that the actual load that's missing and the loop are separated by this ginormous call stack. So do you have thoughts on how you could do this when you have a deep call stack? So like the higher level loop and the actual load that is expensive, there's a big call stack. There are lots of calls in between, function calls.
We didn't implement, like our workloads are always simple, like it only contains one function that has heavy data memory access, and it only contains maybe one loop or one nested for loop. And in that nested for loop, just one instruction that contribute most of the last level cache miss.
Okay, let's thank the speaker and thanks for coming to the session.